Hello everyone, my name's Dr. Vile and welcome to my A-Level Chemistry YouTube channel. The purpose of this channel is all about getting you ready for your A-Level chemistry exams, and this video is going to focus on trends within the periodic table. So we're going to look at things such as trends in melting point as you go across a period, as you go down a group. We're going to look at trends in electronegativity. We're going to look at the chemical reactivity of the group 1 and the group 2 metals as well. So we're going to cover lots of different things in here, and I hope you find it helpful. If you do, please remember to like, subscribe, share with your friends, and keep checking back for more content. Okay, so the first trend we're gonna look at is first ionization energy. So this is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous ions. And the first thing to note is as you go from hydrogen to helium, the first ionization energy jumps massively. The reason for this is that you are adding protons to the nucleus. So the nucleus goes from having 1 proton to having 2 protons, and yet you're adding an extra electron into the same orbital, the 1s orbital. You're going from 1s1 to 1s2. So this electron is being added to the same orbital, which is the same distance from the nucleus, but the difference is the nucleus here, where it has 2 protons, is far more positive, and therefore it has a much stronger pull on this electron. And if it pulls it in tighter, it makes it harder for it to remove. And that's why the first ionization energy increases so much between hydrogen and helium. We then have to explain why there is this massive drop from helium to lithium. Well, you're going from 1s2 on the helium to 1s2, 2s1 for the lithium. So you're adding an extra electron into a higher energy orbital, and this orbital is further away from the nucleus. The atomic radius increases quite substantially when you go from helium to lithium. So whilst you're adding an extra proton to the nucleus, you go from 2 protons in helium to 3 in lithium, the extra electron is so much further away from the nucleus, which means the nucleus has less of a hold on that electron. But also you have what we call the screening effect, the shielding effect of the 1s2 electrons, which provides sort of a barrier between the nucleus and the outer shell electrons, and that makes the nucleus less effective at holding on to those electrons. And if it's less effective, that means that it has less of a hold and it's easier to remove the electron. The next thing we need to be able to explain is why we have such a big increase in general from lithium across to neon. The principle is pretty much the same as from when we go from hydrogen to helium. As you go across a period, the ionization energy tends to increase, and this is simply because we're putting more protons into the nucleus. So the nucleus is becoming more and more positively charged, and therefore it has a stronger pull on the electrons, and the electrons are not much further away from the nucleus. The radius is roughly the same as you go across, so therefore the nucleus has a stronger pull on the electrons, making it harder for them to be removed. However, there are 2 exceptions that we need to be aware of to this general trend of increasing, and that is here. So you can see here it drops ever so slightly as you go from beryllium to boron. Well, if we think about this in terms of the electron configurations, you're going from 1s2, 2s2 for beryllium, to 1s2, 2s2, 2p1. And that's the reason, really. This 2p electron is ever so slightly further from the nucleus compared to the 2s orbital, so it's further out, so the nucleus has less of a hold. And the 2p orbital is higher in energy as well. And if it's higher in energy, that makes it slightly easier to remove, hence why the first ionization energy drops a little bit. The other little trend that we need to be able to explain is, why is there this drop here as you go from nitrogen to oxygen? Why does it decrease in ionization energy? Well, we need to think about the p orbitals here. Nitrogen would be 1s2, 2s2, 2p3. Now, when you have a 2p3, you put one electron in each orbital, all with parallel spins, like so. But when you get to oxygen, you've got a fourth electron, so you put one electron in each box with parallel spin, and then you have no choice but to go back and start double filling the orbitals. So this first box here now has a second electron, and it has the opposite spin. They have to be spin paired. And when you put two electrons in the same orbital, there's a repulsion between the electrons because they're both negatively charged. And this causes it to be slightly higher in energy because of the repulsion between these paired electrons. And that makes it easier to remove, hence the little drop here when you go from nitrogen to oxygen. And then lastly, why does first ionization energy decrease as you go down a group? So if you look, for instance, at the noble gases, you've got helium going to neon, going to argon as you go down the group, and you can see that the first ionization energy is decreasing quite substantially. Because at a glance you might think, well, as you go from helium to neon, you're adding more protons to the nucleus, so the nucleus is more positively charged. However, the outer electrons are further away from the nucleus, so the atomic radius increases, which helps bring down the ionization energy, but also you have an increase in shielding electrons. So if we think of what helium looks like, helium has just got two electrons, so you've got the nucleus here, and then you've got the outer shell electrons, 1, 2. And there's no electrons in between the nucleus and the outer shell, so there's no shielding. So the nucleus has full access to these electrons to hold on to them. Whereas when you get to neon, neon has the configuration 2, 8 in the old Bohr model. So you've got the 2 electrons and then 8 electrons. And what you find is those 2 electrons help screen or shield the outer shell electrons from the effects of the nucleus. And also this radius is getting bigger as well. And then we could keep on going, and it's the same principle for argon. The next set of trends we need to look at is melting point. And we're going to look at the trend in melting point as you go across a period and try and explain what's happening. Let's start with group 2. So let's have a look at group 2 to start with. Hopefully you can see that as you go from lithium to beryllium to boron to carbon, it just increases. Then there's a massive drop in melting point as you go down to nitrogen, then to oxygen, then to fluorine, and then to neon. And we need to be able to explain this trend. So let's give it a go. You'd start off by saying that lithium, beryllium, and boron all have metallic structures. They're metals. And the reason that the melting point increases as you go from lithium to beryllium to boron is because the strength of metallic bonding increases. So lithium forms little 1 plus ions in its metallic structure, and for every 1 plus ion there would be 1 electron. Whereas for beryllium it forms 2 plus ions, and you'd have 2 delocalized electrons for every 2 plus ion. Whereas for boron you'd form 3 plus ions, and you'd have 3 delocalized electrons for every 3 plus ion. So the strength of the metallic bonding increases, and hence the melting point increases. When you get to carbon, carbon is not a metal, but however carbon has a giant covalent structure, either in the form of graphite or diamond, which I'll look at perhaps in a separate video. But because you have this giant covalent structure, there are lots and lots and lots and lots of covalent bonds. Covalent bonds are very strong, and therefore because there's so many of them, to break them all requires such a huge amount of energy that the melting point is really high, and it's really high whether it's graphite or diamond. And then there's this massive drop down to nitrogen, and then to oxygen, and then to fluorine. And these are all simple covalent molecules, so N2, O2, and F2. So you have a covalent bond between, for instance, the nitrogen atoms making nitrogen molecules. Same with oxygen, same with fluorine. And the covalent bond is very strong, but because they're simple covalent, you only have one covalent bond per molecule. So the most significant thing is the van der Waals forces. And the van der Waals forces are relatively weak, and therefore the melting points are so much lower than for carbon. Whereas neon doesn't even exist in molecules, there's no covalent bond there, so it's purely van der Waals forces, hence why it's even lower again. And the same sort of trend can be spotted in period 3. Going from sodium to magnesium to aluminium, they are your metals. And silicon has a similar kind of structure to carbon in that it's a giant covalent structure. So the initial trend starts off the same, then there's this massive drop down to phosphorus, but then there's a little bit of a jump before we go back down to chlorine and argon. So what's the difference between phosphorus and sulfur? Well, phosphorus forms rings typically of P4, 4 phosphoruses in a ring, whereas sulfur forms S8 rings. So you've got twice as many covalent bonds and you've got stronger van der Waals forces, hence why there's a slight increase from phosphorus to sulfur. However, these are both still simple covalent molecules. The next trend we're going to look at is the reactivity of the group 1 metals. So lithium, sodium and potassium. Those are the main ones that we focus on at A level because they are the safe-ish ones that you can use in the lab and do quite interesting demonstrations with. The general trend is that they get more reactive as you go down the group. Let's just try and explain that first before we look at the reactions. Let's understand this. So lithium has got 3 electrons. So it would have 2 in its first shell if we're just using the Bohr model, and then 1 in its outer shell. So lithium is very reactive because it wants to get rid of this outer shell electron. It wants to form a stable ion by getting rid of that electron. Now sodium is very similar in that it has 1 outer shell electron that it wants to get rid of. So it's very reactive because it wants to lose this outer shell electron. The difference between lithium and sodium, and you could extrapolate this to potassium, is hopefully you can see that this outer shell electron is further from the nucleus. And remember, the further the electron is from the nucleus, the less hold the nucleus has on that electron. So the sodium nucleus has less of a pull on this outer shell electron, it can hold on to it less tightly, but also you have the shielding effect of these inner electrons, which is greater. So this outer shell electron can be lost more easily due to greater shielding and a greater atomic radius, and those two things outweigh the increase in nuclear charge as you add more protons to the nucleus. And that's why sodium is more reactive than lithium, and that's why potassium is more reactive than sodium. So all of these metals will react with oxygen, and they'll react with oxygen more easily as you go down the group. So let's just take one as an example. If you take lithium, lithium is a solid, react it with oxygen, which is a gas, and you form lithium oxide, which is Li2O. The lithium is effectively rusted there. And if you're wondering where that formula came from for lithium oxide, lithium forms 1+ ions, Li+, oxygen forms O2- ions, and therefore you need 2 lithiums for every 1 oxygen. This equation isn't balanced. You've got 2 oxygens on the left and 1 on the right, so you need to have 2 lots of the lithium oxide, and that would leave you with 4 lots of lithium over here. So they'll all react with oxygen, and the reactivity increases as you go down the group. And what happens is these lovely shiny metals start to become tarnished and grey as they build up, like the lithium oxide or the sodium oxide on the surface. It's a bit like rusting, in other words. And the group 1 metals will all react very violently with water as well. And as before, the reactivity increases as you go down the group. So the general reaction, if we just take lithium again as the example, you've got lithium, which is a solid, react it with some water, H2O, which is liquid. You form lithium hydroxide, LiOH, and because there's an excess of water, that will be in solution, and then you form hydrogen gas. So what you would expect to see is fizzing or bubbling on the surface as hydrogen is produced. However, hydrogen is very flammable, and there's quite often enough heat generated from this reaction that the hydrogen will ignite. And when the hydrogen ignites, it causes basically the flame test for lithium, so you end up with a red flame colour. So what you'd expect to see is bubbling, perhaps a small mini explosion, which would give a red flame colour. The lithium also floats on the surface of the water. And to balance this, you'd need to put a 2 in front of each of these. If you replace lithium with sodium, the same chemistry will happen. The only difference is you'd form sodium hydroxide instead. And when the hydrogen ignites, you'd get the flame colour for sodium, which will be a yellow-orange flame. And this reaction happens far more violently, and the hydrogen is far more likely to ignite by itself. And sodium floats on the surface of the water. It gives a really nice shiny little ball. And if you replace it with potassium, same kind of chemistry again, although it's even more reactive. And when the potassium ignites, it'll go with a violet flame colour. So we're going to move away from group 1 onto group 2 now, and we're going to look at the reactions of the group 2 elements with water. So the group 2 elements will react less readily with water than the group 1 elements, and the reason is they've got 2 electrons in their outer shell as opposed to 1 electron. So it's harder to lose 2 electrons than just to lose 1. However, the same trend applies in that they become more reactive as you descend the group. So if you take magnesium, for instance, magnesium reacts only with very hot water or steam. So you have to really heat the water up for any reaction to happen. Whereas if you go to calcium, calcium will react with cold water, and the reaction is much quicker than for magnesium. And what happens is the water turns cloudy, and that's due to the low solubility of calcium hydroxide. The solubility of the group 2 hydroxides increases as you go down the group. And then when you get to the elements at the bottom, strontium or barium, they will react very easily. And you form an alkaline solution, since strontium hydroxide and barium hydroxide are both soluble. So they'll all react with water, but the ease with which they react with water increases as you go down the group. And the solubility of the corresponding hydroxides increases as you go down the group. And on this page here, you can see the equations. I'm not going to go through them in any great detail. You can pause and have a look at them if you want to. But just notice magnesium hydroxide, calcium hydroxide are both solids, whereas as you go down the group to strontium hydroxide and barium hydroxide, they are aqueous. And just like with the group 1 metals, you form hydrogen gas as well. And then the last reaction that we're going to look at in this video is the reaction of the group 2 elements. We should say here group 2. With dilute acid. You would be silly to try concentrated acid, so we're talking dilute acid. And the chemistry here is if you take a metal, react it with an acid, you form a salt and hydrogen. The way I would say to remember that is it's the MASH reaction. Metal, acid, salt, hydrogen. And as before, the reactivity increases as you go down the group. So calcium will react more vigorously than magnesium, for instance. And then I've included a couple of examples here. So magnesium reacting with sulfuric acid to form magnesium sulfate and hydrogen. It's worth noting that the choice of acid will dictate which salt you produce. So if you have sulfuric acid, you form the metal sulfate. If you use nitric acid, you form the metal nitrate. And if you use hydrochloric acid, you form the metal chloride. And in all of these reactions where the metal reacts with the acid, they are redox reactions. So oxidation and reduction are taking place simultaneously. And the reason for that is the metal is going from 0, as it's an uncombined element, to +2 in the salt. But then the hydrogen is going from +1 to 0. So where the magnesium is being oxidized, the hydrogen is being reduced because the oxidation number is decreasing. And as we say, these metals get more reactive as we go down the group. Well, thank you for taking the time to watch this video. I hope you found it helpful. If you have, please remember to like, subscribe, and keep checking back for more content. See you next time.